Hello, everyone. Welcome to our panel on green qubits, quantum innovation for sustainability. And maybe before you come up, I want to quickly share why this panel is so important and where the inspiration for this panel came from. And it stems from an analogy in the AI world, because in the AI world, we often distinguish between green AI, like how can we reduce the environmental impact of AI itself, and also AI for sustainability, which looks at the use cases and the challenges, how they can be tackled with the help of AI. And today we will ask the panelists the same questions, but for quantum. Can quantum itself be green, and where can it actively contribute to make the future more sustainable? And I'm delighted to be joined by this awesome lineup of panelists. So first of all, Ewald Munz. He's the leader in manufacturing and sustainability at Cisco. He's driving energy efficiency and quantum-based energy management initiatives, and we are delighted to hear more about that. So please come on stage. And then next, we also have Dr. Corey O'Meara. He also introduced himself, I guess, very well in the previous talk. So he's chief quantum scientist at E.ON, and he's exploring quantum applications in the energy transition and for smart grids. And then we have Dr. Renata Jovanovic with us. She's an advisor and board member with over 25 years of experience in the industry, and she's focusing on deep tech for sustainable materials discovery and innovation ecosystems. And last but not least, Dr. Ursula Maria Meyer. She's a computational scientist, entrepreneur, and AI quantum consultant with a focus on high-performance computing. So please give a warm applause for all the panelists, and then we can dive right into the panel. So the plan for today is to start a bit with quantum for sustainability, then dive into how quantum itself can be green, talk about adoption challenges, and also give an outlook for the future. And the first question directly goes to Ursula. It's good that you're next to me already. So where do you see an advantage of quantum over classical high-performance computing when you look at the sustainability challenges we face?
This is a complicated question all in once. So I think at the moment, quantum computing, high-performance computing, we are first beginning to build quantum-centric high-performance computing, so adding so-called QPUs together with CPUs and GPUs. And the advantage, or the hopefully coming advantage, will be that the QPU then overtakes specific computation where it's suited for, which can be performed in much faster than a CPU or GPU could do it.
Yeah.
And hopefully also the entire manufacturing operation and
logistics
other processes will also, which of course require energy and water and a lot of resources, will still make it more resourceful for us, so that the application also helps to improve sustainability. And there are a lot of application areas, like energy or logistics, material science,
exactly.
finance.
And that would be also like the best. You already do the moderation for me. Like the follow-up question goes to Carrie, because you mentioned that you see the energy grid as the largest human-made structure, and you are like someone who's really enthusiastic about using quantum for making a real difference there. So how do you see quantum as a positive impact bringer to renewable energy integration, for example? Can you sum that up for us?
Yeah, I mean, so I just gave a talk about one small example, about how to make use of locally generated renewable energy, and I think the main thing is the energy grid was built over many decades, and if we think of the energy demands that come in the next decades, we don't have enough infrastructure to actually transport that much, or to generate more electricity. You have to go and use local renewable energy sources. So it's not an option actually to make use of the local renewable energy. So as we move to this digital part of the grid to enable these millions of injections locally, we need super powerful tools to do that. And we see quantum as just a hammer but for the right things. No, not a hammer for everything, but just for the right nails. And that's what we're working on, is to find out, you know, what are the right optimization problems, what are the right hard optimization problems to run it for. Yeah.
Great, perfect. And maybe, Ewald, you're also looking into energy efficiency because you're part of a consortium at the High Performance Computing Center at the University of Stuttgart. And as I know about the project right now is that you're researching energy efficiency there. And maybe you can share with us what Quantum is doing to contribute to this goal.
Yeah, first of all, I like your question because it's a real world, very concrete question, and maybe beyond the typical, let's say, academia challenges. And as you may know, there's always this friendly competition between software and hardware in quantum, who is better, or who needs most, and all this. And I would like to, let's say, highlight both elements here. Yeah? So you mentioned the project with the HLRS, the High Performance Computing Center in Stuttgart. So we work here with our partner Qipu Quantum. So they bring in basically the algorithms expertise in there. There was just before panel or discussion with the Johannes from Qipu. So we basically optimized the scheduling of workloads. So you can imagine there are like thousands and thousands of workloads, some very process intensive, some very light process intensive. And of course, you optimize this with the help of Qipu Quantum. So this is the software part. Yeah. Now, if you think about the hardware part, there was this morning a presentation from Professor Krüger from the FKI, who shared his vision of distributed quantum computing. So it's basically very similar to the rise of the internet. So there's not, let's say, one monolithic server. It's a distributed landscape of different quantum computing centers. And of course, the key is then communication, how all these quantum centers communicate via a very reliable and strong network. And here I would highlight, for example, the innovation from Cisco, who has developed a quantum entanglement chip, which is highly energy efficient. Just to give you some statistics, it consumes 1 megawatt of energy, so very, very low energy efficiency, and it works at room temperature, so it doesn't need this typical kind of cooling. Yeah? So both software and hardware, key elements of energy management, which I believe will be a game changer for quantum computing.
Perfect. And last but not least, we know from the previous exchange of emails, Renata, that you are looking into sustainable by design molecules and catalysts, and that it's very important from your perspective. So why do you see quantum chemistry as one of the most promising routes for sustainability?
Yeah, so I believe that in the future we need more smart materials, and the way how we design materials, and I'm guilty of that as well in the past, is not really sustainable. So we need new tools, and I've just shown maybe a couple of minutes ago that we need to understand better what do we get out of reactor before we put even anything in it. And this is our opportunity actually to do sustainable by design. We can test something in silico using, I would say, more hybrid approach where we have quantum computing, where we have high performance computing, AI, Gen AI all together, to see if this material is sustainable even before we put anything on the bench. And I truly believe that this is the way how we need to design materials for future mobility, for future of electricity also, if you think about nuclear fusion or all these kind of things. We simply need to change the way how we design materials. And quantum is definitely a piece of this equation.
Great, perfect. Are there any other use cases maybe you want to share, like an open question before we would move to green quantum?
Yeah, I think in logistics and supply chain, this is a field which even AI is not yet exhausted, but quantum computing could even add in, because we have a lot of combinatorial optimization problems to be solved and an enormous amount of problems, not only a few which could be optimized, and this has, of course, a very, very direct impact on sustainability, reducing transport, storage, overstocking, understocking, waste. A lot of stuff has to be thrown away. It cannot be sold like for 10 years. So this is a field where quantum computing could really also contribute a lot to sustainability.
And also recycling. I mean, we have spoken about raw materials now, but recycling is a very complicated process because as opposed to dealing with raw materials that are native raw materials, you never know what you're going to get as a raw material. So the number of variables that you have in raw materials, in how do you set up your production process based on these differences that you get is enormous challenge. So again, this hybrid approach, quantum AI and high performance computing, will be great for chemical but also mechanical recycling. So that's not designing from scratch, but using what we have in a better way.
Perfect. Yeah, thanks for the first theme. Then we maybe move on to the green quantum as the next big topic for the panel discussion. So maybe directly again a question to Ursula. Quantum hardware itself requires, of course, resources to build a quantum computer, and yeah, also to run it and so forth. But how does it compare to classical computing? So maybe you can compare it a bit. Like, is it more? Has it an advantage to use a quantum computer now in terms of energy needs, or?
So actually, the computation itself is very, very efficient. But unfortunately, we have stuff around.
Yes.
So most of the quantum technology at the moment, we have to cool down to either 15 millikelvin or 4 millikelvin. There are approaches like also Ewald already mentioned. For example, photonic quantum computing can be run at room temperature, but not all components. So there's mostly still this photon detector which needs cooling. So we have to consider this, that we have to put on energy, we have to bring up all this energy to cooling or work more on full room temperature computation. And then for the cooling, it's usually gases who are used and other resources, and we still have to build semiconductor chips for the photonic quantum computing. And also the manufacturing process usually requires more energy and is more carbon intensive than actually the entire operation. So it's not, so far I think we start looking at the operation, but we still forget
we have to look
more forget about the manufacturing, and as Renata already mentioned, also then the recycling and the disposal. E-waste is also a very, very big problem. So there are some additional challenges we have, but also already ways where we work towards solution. And in academia, there are also frameworks like carbon, so architectural carbon design frameworks where you can really, or you guide it through the entire manufacturing and operation process, and it helps you to identify the sources of where you produce a lot of carbon, where you need energy, and so on. So there is help, help available, but I think it's still complicated because we do not have like good metrics and benchmarks. So in classical computing, we would have watts per flops, but in quantum computing, we don't even have a flops equivalent. We have, I mean, IBM has quantum volume. I'm sure other companies have other metrics to measure their power capability of quantum computers. And then it's, of course, now we come with carbon use and energy usage. And yeah, we would have to establish metrics and benchmarks and also add this to speed and efficiency. Yeah, and so to have a broader picture of the entire development.
Really important. And okay, you want to add it?
Can I add to that?
Yeah, sure.
So no, that's great points, and I think another aspect of that is about what the application is actually at the end, right? So, like. Ideally, you want to run a quantum computer on use cases. Let's just talk about optimization for the sake of it. If you have a really hard optimization problem that would take, weeks, let's say, running on a supercomputer, that's a lot of operations to reach the solution, right? Now, if you compare that to the energy requirement to, let's talk about superconducting chips for now. So you cool it down, and then the operating sort of energy is quite low, actually, after you've kind of cooled it down. And you know, also every university lab in the world, they all have superconducting devices. So like every NMR machine in biolabs, I mean, these are all supercooled using helium. So the argument is that, okay, that's kind of everywhere and people don't really think about it. So if at the end of the day you're solving a problem that would take weeks or months running continuously on a supercomputer, then there's a clear kind of energy quantum advantage kind of at the end of the day. But the thing is to find the right problems where that happens, right? So I think that gets, at least I submitted many papers to certain journals, and then they say, yeah, why are you trying to use quantum to solve this problem? Because quantum uses so much energy, and you're trying to optimally reduce energy, so it's a chicken and egg problem. And then we have to sort of respectfully disagree with them to get it published, basically. But you know, this is like a common thing. So I want to say it today to get the word out there that it depends on the problem.
Yeah, also, if we have an application which then in turn saves a lot of carbon, like we optimize transport of a huge e-commerce shop, then this also has to be taken into account. So it's the manufacturing, the operation, and then also the application. So all together has to be looked at.
Yeah.
And then, it needs to be summed up. And
perfect. Yeah, maybe Ewald, can you add a perspective from the research project to it? Like, how do you consider the green aspect of the hardware when you build up a data center there?
Yes, I mean, you said the right word for select the tasks. Yeah, so for select the task, it's really a game changer. So we're talking here about these three metrics: energy cost, energy efficiency, and carbon footprint. That's basically an improvement with, let's say, level 10 to 10,000, depending on the task. Yeah, so it's really a game changer if you basically replace tasks of traditional data centers with a quantum computer. Yeah. Yes, so this is a classic hardware challenge. Yeah.
Yeah, and the easy win is, of course, to use green energy to power your data center.
And of course, it's a classic business case. Yeah, if you talk about energy costs. Yeah. This is a business case for the companies. Yeah.
Okay, then maybe we can shift a bit the focus also back again to the material and resource perspective to give Renata a chance to share her perspective. So what challenge do we face in making quantum hardware itself more sustainable, maybe also with the materials that go into it?
Yeah, I just wanted to say it's all about materials, right? At the heart is new materials that we need for development of new hardware. But what comes to my mind is very consulting statement. So we need to think really end to end. You can only compare these things if you're not staying in your little soup and your little teller. You can only compare it if you're really looking end to end, if you're looking into the whole life cycle of this solution. So how many times you're going to use quantum, how many times you're going to use high performance computing for these type of problems. So when you put all together, this is where we kind of get the real balance. Is it worth it, or for what type of problems? And when I think about materials, we need everything from cooling data centers. We need new coolants that are better than what we have, like liquid cooling. I'm talking about liquid cooling. We need also completely new materials for quantum. Maybe now we are talking a lot about superconducting qubits, but how about neutral atoms and trapped ions? These are also solutions that require new materials. So we can use quantum to help us to design better quantum, as we are using AI to help us to design better materials for AI. And I just mentioned a couple of minutes ago, if we think about nuclear fusion, this might be the future of how we supply all these huge data centers and GPUs and who knows what in the future with energy. So Microsofts of this world and AWS, there is simply not enough nuclear power. Even if they want to buy every single nuclear power on the market, there is not enough of them. So we need to think about future energy types as well, and also use quantum to, let's say, simulate very complex processes happening in plasma and all these kind of things that we need for the nuclear fusion.
And maybe one follow-up, is there also like certain materials like rare earth materials that that we run into a scarcity problem when we want to scale quantum and want
Yeah,
to
it depends which, if you're, these type of problems are more related to superconducting qubits. We are using existing technology that we know there are limitations of existing technology. For other technologies, we need to even discover what kind of atoms are best atoms for neutral atoms, quantum computing. So it's, yeah, depends which kind of technology you select. You might have different problems with rare earth materials or other type of materials that you would like to use to produce qubits.
Okay. And now we have a little question to the audience to see if you are still awake. So who of you have heard of the Jevons paradox? No one? Okay, maybe you heard about the rebound effect? Yes. Okay, that's basically the same. And I wanted to raise that because if you talk about sustainability, you often don't, you come along this effect, because this Jevons paradox says that if you have efficiency gains, it paradoxically increases the total consumption and does not reduce at what you want with efficiency gains. And if you have the example of computing, this means we have more efficient computing with quantum, for example, but this drives higher overall demand in computing, like we want to solve more complex problems. So I ask you the impossible question, so how would you resolve that paradox here, and how can we contribute to genuine sustainability here? Like maybe you have a thought about that. It's a tough question, I know, but I don't want to...
Maybe I would say it's more like a mindset problem, because let's say if we talk about sustainability, it's very often about how we can save something and how we can save this % and that % and how we can be more thrifty and switch off the heating and these kind of things. But I would say with quantum computing, it's more like a change of mindset. It's more like about innovation. And we don't talk about the 10-20% savings. We talk about 10,000% or more, or a completely different kind of universe, I would say. So it's this mindset attitude, I would say. Innovation, not this kind of savings kind of approach.
I would also go for innovation.
Yeah.
Because we know that traditional, for example, material discovery in let's say producing of fertilizer, we know that this process releases huge amounts of CO2. 2% of CO2 released on Earth are coming from this particular process. And if I use quantum computing to discover better process for the same reaction, let's put it that way, I think we are only winning in that sense. We just have to be quite bold, and we will get out of these, let's say, interesting problems that we have. If we are just drifting around and we look this little tiny problem, and we need to look this other tiny problem. So looking just tiny problems is not going to solve our sustainability problem. So we need to be very, very bold to solve the sustainability challenges that we have. So I think we are not going to touch this thing if we are bold enough and innovative enough.
Okay, great, perfect. Then let's maybe move on to the next theme for this panel, which would be the adoption challenges. And maybe also talking a bit about the ecosystem needs. And my first question goes to Renata again. What role does collaboration across industry, startups, and all these players that you meet today at such a conference play to scale quantum solutions for sustainability?
Yes, as opposed to AI that existed for many, many years in, let's say, ivory towers of universities and so on, and then came to industry, quantum is very interesting. Something is happening that we are discovering hardware, software, and use cases in parallel. And I think that's unique technology. There is no other technology that has done these type of parallel discoveries. Let's put it that way. I think it's very unique in history what we are going to do with this tech in the future. So we have to bear in mind that we are just seeing the light. I always say, like, this quantum technology is like we are driving a car at night. So, and we have this lights in front of us, so we see the road a little bit. We don't see the whole road. We just see the part of the road and have idea where this road is gonna lead us in the future. So it's it's worthwhile observing, let's say, and imagining how the future and how the sustainability with this technology is going to look like. We don't know yet, maybe just small portion of how we are going to use it for this attacking sustainability challenges.
Yeah, that's an amazing analogy with the light. I love it. Next question, Corey. You said you've been exploring use cases since 2020, so you were one of the early adopters in the industry. And maybe you can share some of the biggest bottlenecks in the adoption that you saw in the last years so that we can bring quantum to the real deployment.
Yeah, the bottlenecks in the adoption. We've been looking into things for 5 years around now. It was challenging at first to even start looking into it. So even the adoption inside our unit was sort of difficult. Yeah, so I mean, it started as a side job that I kind of did after work, kind of. So it was a very small team, kind of a skunk works sort of setup, and it was difficult to even find the right problems. But it spun out of our data and AI department. So the nice thing is that we had like 140 data scientists, data engineers, building internal products for the different E.ON business units across Europe. So they basically saw, okay, at scale, what we're doing now won't work. So the adoption kind of grew out of that, saying, okay, how can we make this into a quantum algorithm, or is there kind of a potential there? Now, for company-wide adoption, that's now the next step. So the adoption inside our unit or our department is clear, but we only know as much as the domain experts know. So the colleagues who really work for parts of managing E.ON's grid, for example, they're the real domain experts. Yeah, so you have to basically educate the right people, both engineers who know the technical details and management in the different areas of our business, in order to figure out like where is the real bottleneck going to be. And sort of a bit of a sad thing about our community is there's a lot of hype in quantum, and a lot of people have preconceived notions of what quantum computing is. And so you have to educate people to show what can you do today, what can you do tomorrow, what is hype, where's the real ability lie. And if you really want to find a quantum advantage, you need that aspect of it. So right now, that's kind of where we're at, is the adoption of educating the colleagues in a large corporate that have those challenging problems, but it's hidden. Yeah, it's really hidden information, and we're trying to kind of scrub it away to kind of get to the nitty-gritty details. And so, yeah, that's basically where I think adoption is, at least from my perspective.
Do you want to add something from your perspective in the industry?
I think you said a key point, education. So I think it's really important to get up to speed on this topic. Of course, it's not so easy, can be very, very complicated. I mean, I have no maths or physics background, but I found it actually quite easy. Of course, with this conference, and there are many courses available, partially also free from Fraunhofer and other institutions, to really learn the stuff. And then, of course, you have to find, let's say, your personal sweet spot, how you can connect to this topic. And for example, from Cisco, it's a networking company, and their sweet spot is obviously a networking infrastructure, and that's why they came up with this innovative quantum entanglement chip for the communication. Yeah. So education and finding your sweet spot, I think, are the adoption challenges. Yeah.
Yeah, and I just thought about in the AI use case world, people often struggle with the hidden debt in digitalization, like the data is not available and so on. Quantum is not inherently that data intense sometimes, but do you struggle as well with the data problem in quantum applications, or is that not a problem?
I mean, you can only fit a little amount of data on today's quantum computers.
Yeah, of course.
So the challenge is to reframe your problem such that it's small enough to run, but it's still complex enough and reflects the actual business use case.
Okay.
And that's the whole, and that comes down to machine learning or molecular simulation or even quantum machine learning. That's a whole other kind of can of worms. And so I don't see a problem with the amount of data.
Maybe just to catch up on that kind of worms. So you have very complex structures in our materials, and one of them is, for example, metal organic frameworks that we will use for direct carbon capture from air. Those are humongous structures, and we can definitely not tackle the whole scale of it with the quantum at the moment. But what we can do is isolate these repeating units. So the structure is made of repeating units, as everything in nature is. So we can play with this repeating unit just to figure out, is it better to have this atom metal or the other metal, or what are the surrounding atoms, to play with it to see which one will give us the better absorption of CO2 and not absorbing water. That's not the goal. On this smaller scale. So just isolating things to figure out, okay, can we use it for this purpose? That's exactly what we are talking, like making the problem smaller so you can handle it with current quantum computing. I think the biggest problem in adoption is in people's mind, because a lot of people are thinking like, oh, yeah, this NVIDIA guy, Jensen, said, oh, it's going to be 30 years from now. As a CIO, I don't bother with this. As an R&D head, like, why should I bother? That's the biggest mistake, because you should play with it right now. Because if you're not playing, I'm consultant in nature, I have done some wargaming on this. Companies who are not prepared, as good as E.ON is, for the future, they will not be able to pick up. So early adopters of quantum computing will get all the benefits. Just imagine if I, with my little playing around with molecules, I discovered a new drug, for example, my P&L is going to boom extraordinary because I use quantum computing and I understood how to design new material. My competitor, who is not even starting yet, will have a big problem to catch up my gazillion of dollars that I'm going to have on my P&L. Yeah. As simple as that.
Yeah, that's true.
That would be nice, yeah.
You'll get there, don't worry.
Yeah, the gazillion dollar metric. Yeah.
We should dream of something, yeah. The stakeholder buy-in is very important, and maybe you can share a bit of your perspective on that, because you do a day-to-day consulting work in that area. So maybe how you can share how you convince stakeholders these days to invest in quantum right now and use it maybe also for sustainability.
Yeah, it's much easier to convince them to do an AI solution than a quantum solution, since they are already used to. But as Renata said, I mean, we have seen this with AI. It took companies a couple of years. I mean, most started like, let's say, 8 to 10 years ago, but it took them a couple of years to get used to them, to make actually AI use cases run. Now it is, for most companies, quite good, and they're really fast in adopting. LLM came, LLM assistants, now it's AI agents, so now they jump in very quickly, and mostly they manage to realize something. But with quantum computing, it's still complicated, so you can convince them. Now it would be the stage to do the small projects, the research projects, and look for the use cases where then it can be scaled up and maybe also combined with AI. And because, yeah, if not necessary, it takes a couple of years to get used to find the right people, to set up the right teams. It can also not be a separate silo, so there needs to be set up the collaboration within the company. The management needs to be educated, so this takes a lot of time. And if IBM then has its working quantum computer or industry-ready quantum computer in 4 years, it will be too late to get into it. So if you start now and industry-ready quantum computing is available in 4 or 5 years, then it would be now the right time to do it. And in 4 or 5 years, it's then a bit late. I mean, it's still possible, but you will have other companies, being ahead and basically being able to jump into this right now and also use it.
That's a good call to action, and for the looking ahead, which will be like the last thing we talk about. And one question that came up to my mind here, and I'm very excited about looking into the future there. So we know that there are different types of hardware for quantum computers, and you know them a bit, but maybe you can share your perspective on which type will win the race to become the most sustainable quantum computer type. And maybe you can also elaborate, you did it at the beginning a bit already, like what criteria are important to actually define what will be a green quantum computer? Do you look on energy efficiency, resource intensity, scalability, or the end-to-end life cycle? So maybe to sum that up a bit under this question. It goes to everyone, so don't be shy.
Maybe I can kick it off. So I think this, if we learned anything from AI and the way how we deal with it, this end-to-end thinking is a must. We will not move forward if we are not thinking end-to-end. So, I don't know. I believe, I don't know, but I believe that quantum is going to be, for certain applications, we will have certain type of certain modalities. And maybe for material design, it's going to be neutral atoms and trapped ions. For banking, is going to be superconducting qubit. We don't know that at the moment. But I believe it makes sense, because if we're talking about material design, we're talking about atoms, quantum mechanical systems that we are going to model with quantum mechanical systems, which is ultimate goal of the whole game, right? And maybe superconducting qubits are going to stay there for optimization problems, so for banking, for efficient energy grids. So this is where I think it's going to crystallize itself when we get to the, let us say, larger number of qubits. I'm not talking like 200s, I'm talking about plus.
I mean, talking about hardware, I mean, myself, I wouldn't dare a prediction which hardware will prevail. I mean, if I would know this, I would buy some shares, of course, nowadays. But in my opinion, the real game changer is, or will be the software behind. And if you look, let's say, how the internet developed nowadays, I mean, all the hardware behind nowadays is more or less a commodity, yeah. And really the algorithms, the software drives the innovation, and not so much the hardware, yeah.
I mean, now it's the time to actually, since the hardware is not fully developed, to actually look into it and develop sustainable hardware, to have the entire carbon energy through the entire life cycle recorded and also optimized. So that's now a good point in time, and maybe look at use cases in your company which contribute to sustainability. And also sometimes we have this feeling that we have to look here for sustainability, that's only costs, we cannot afford it. But very often, if we actually contribute to sustainability, I mean, in logistics and supply chain, it's very open. We also save a lot of money. So that's actually a very good way of selling AI solutions or quantum computing solutions in supply chain and logistics, is because it really also helps companies to save a lot of money and contribute to sustainability. So that is also something I think we have to keep in mind, that it not only costs, so it also saves us costs.
One small point, I think that we first need to develop the technology and actually get to fault tolerance first. The iPhone or the iPod, when it came out, Apple wasn't really talking that much about sustainability at the time. But in the life cycle of a product, as it matures, but we have a lot of work to do to even get the quantum computers there. I mean, we should have sustainability sort of in the background, of course, but let's focus on that and get the the sustainability aspect more on the end of that cycle, which is like the application side of it, to save first, I would say.
Okay, perfect. So thanks a lot, everyone, for your insights. It was really nice talking about sustainability with you. And yeah, to sum it up, we've explored all the use cases where we can use quantum for sustainability, looked a bit on how quantum itself can be green. And yeah, maybe the speakers are available later on so that you can also discuss more about it. And let's hope that the challenges are smaller and smaller the next year so that we really can tackle it and be quantum green in the future. And yeah, so thanks everyone in the audience for being here, and yeah, see you around.
May I make a final point? We
One
discussed
final point?
last night of some quantum
no.
joke. And I thought very hard about
the quantum joke. And I googled for quantum jokes, and the first one was a sexist quantum joke, and then I stopped.
No, that's not sexist. So I thought it's actually quite difficult to make a quantum joke because of the superposition capabilities. It's funny and not funny at the same time.
Yes, okay, that one is the good one. Okay, thanks. Yeah, we are done.
Let's get a round of applause.